Welcome to The Explainer. Today we're taking a seriously fascinating journey inside the invisible semiconductor magic that flawlessly controls our everyday electrical devices. We flip switches, we dim our living room lights, we turn down the ceiling fan, and we rarely stop to think about the incredible physics making it all happen behind the wall. Well, today we're going to unpack exactly how that works by looking at three absolute titans of power electronics.
Okay, let's dive right into this. To understand the sheer scale of what we're talking about, we kind of have to look back. Ever since the 1950s, the electrical industry has undergone a massive revolution. By the time this technology fully matured, over 100 million of these semiconductor devices were being manufactured every single year. 100 million. Why? Because engineers desperately needed a way to control huge blocks of power reliably, efficiently, and on a global scale. So, here is our roadmap for today's explainer. First, welcome to power electronics. Second, meet the TRIAC. Third, the DIAC trigger. Fourth, unijunction transistors explained. And finally, number 5, real-world applications.
Section 1. Welcome to power electronics.
So, the core engineering problem of power electronics basically comes down to control. If you want to dial in the speed of a heavy-duty industrial motor, or honestly just dim the lights in your house, you have to control alternating current. Doing that with old-school electrical resistors is a terrible idea because it wastes massive amounts of power as heat. To control these big blocks of AC without wasting all that power, engineers initially relied heavily on the SCR, or silicon-controlled rectifier. If you think of semiconductors as electrical valves, an SCR is brilliant, but it's fundamentally a one-way street. It only conducts current in one direction, meaning it can only control half of an AC cycle. But alternating current, by definition, flows in two directions. So to achieve really fine, seamless control without wasting energy, we needed a revolutionary two-way valve.
Section 2, meet the TRIAC.
And this brings us to the undeniable hero of alternating current control, the TRIAC, which stands for Triode AC Switch. It's a 3-terminal semiconductor switching device that completely masters AC power by conducting in either direction. And this brilliantly illustrates how it works. Notice how the triacs acts as a highly precise gatekeeper for a standard sine wave of alternating current. It doesn't just block or allow the whole wave, it can actually be timed to only pass specific, shaded portions of both the positive and the negative half cycles to the load. By slicing the wave up like this, you control the exact amount of average power delivered, and you do it all with virtually zero energy lost to heat.
Now, what's really interesting about this slide is that if we look under the hood, we see that while the TRIAC is a complex 5-layer device structurally, electrically it operates essentially as two SCRs wired in inverse parallel. It's literally two one-way valves pointing in opposite directions, cleverly combined right into a single crystal and sharing one unified gate lead. This elegant internal geometry is exactly what allows it to seamlessly conduct in both directions.
So how do we actually operate this magical valve? The circuit action happens in 4 precise steps. First, the gate terminal receives a small trigger current. This lowers the breakover voltage, which is effectively step 2. In step 3, the TRIAC fires, rapidly switching from an open circuit to conducting massive amounts of AC power. But here is the truly fascinating twist in step 4. Once the TRIAC fires into conduction, the gate completely loses control. Seriously, you cannot turn it off using the gate. The TRIAC will only stop conducting when the main current naturally drops below a specific holding value, which, conveniently for us, happens every single time an AC wave crosses 0.
Section 3, the DIAC trigger.
Now, there is a bit of a catch here. For a TRIAC to smoothly control power, especially in everyday things like light dimmers, it needs to be triggered at the exact same point during both the positive and negative cycles. A simple resistor just won't cut it. The TRIAC needs a precise, reliable sidekick. Enter the DIAC. It's a 2-terminal, 3-layer bidirectional switch. Looking at its basic PNP construction, do you notice what's missing? There's absolutely no base terminal attached to that middle layer. And unlike a standard bipolar transistor, the doping concentrations on the outer layers are identical. This perfect symmetry, paired with its distinct symbol, which kind of looks like 2 diodes pointing at each other, means the DIAC behaves exactly the same way regardless of which direction the current is trying to flow.
So the crucial point is how it reacts to voltage, which is mapped out in these VI characteristics. The DIAC acts essentially as an open circuit, just blocking current, until the voltage across it reaches a very specific threshold, usually around 30 to 50 volts. We call this the breakover voltage. Once it hits that exact point, in either the positive or negative direction, boom, an avalanche breakdown occurs. The device's resistance suddenly drops off a cliff and it fires a sharp, strong pulse of current. This sharp pulse is the absolutely perfect trigger to reliably fire our TRIAC.
Section 4. Unijunction transistors explained.
While the DIAC is fantastic for basic triggering, complex industrial power systems require absolute precision timing, and for that, engineers turn to a totally different, highly specialized component, the unijunction transistor, or UJT. Now, despite having the word transistor right there in its name, structurally it's actually a double-base diode. It consists of a lightly doped N-type silicon bar with two base contacts at the ends and a heavily doped P-type emitter fused right into the side of it. This creates exactly one single PN junction.
What makes the UJTs so incredibly useful for timing is a built-in mathematical property called the intrinsic standoff ratio, represented by the Greek letter eta. Because the emitter is placed partway along the silicon bar, it naturally divides the internal resistance. This specific ratio, which is usually between 0.51 and 0.82, dictates the exact peak point voltage required to turn the device on. It's literally built right into the physical silicon, making it exceptionally reliable.
Let's move to and see how this builds directly into the UJT's true superpower, the negative resistance region. When the emitter voltage hits that critical peak point, the UJT fires, and the internal resistance between the emitter and the first base suddenly collapses. As a result, the current shoots up while the voltage actually drops down to a valley point. This highly stable, extremely predictable collapse in resistance makes the UJT the undisputed king of precision trigger circuits.
Section 5. Real-world applications.
Okay, so all of the silicon physics and negative resistance stuff is fascinating. But how do the TRIAC, DIAC, and UJT actually team up to control the modern world? Well, the applications are literally everywhere around you. They are the hidden mechanics and smooth lamp dimmers, allowing you to turn the lights down low without the switch heating up and catching fire. They control the heat output in your electric heaters. They provide universal motor speed control. And by the way, this phase control technology is exactly how your ceiling fan changes from a gentle breeze to high speed, seamlessly, without wasting expensive electrical power as raw heat. They even act as completely solid-state, high-power industrial AC switches that never wear out because there are absolutely no moving mechanical parts to break.
A perfect example of this teamwork is the UJT relaxation oscillator. Just look at the beautiful simplicity of this circuit. A capacitor slowly charges up through a resistor. The very moment it hits the UJT's specific peak point voltage, the UJT switches into that negative resistance mode, instantly discharging the capacitor. Then, the UJT shuts off, and the whole cycle repeats. This simple action generates a perfectly timed, continuous sawtooth wave, which can be precisely tuned to trigger our DIACs and TRIACs hour after hour, year after year.
These three tiny, unassuming components, the TRIAC, the DIAC, and the UJT, have formed the bedrock of AC power control for over half a century. They are a true testament to the sheer elegance of semiconductor engineering. But as we transition towards smarter grids, totally renewable energy, and massive electric vehicle infrastructure, we really have to ask, with this foundational technology reliably controlling our world for decades, what invisible semiconductor magic will define the next major leap in power electronics? Thanks for exploring this with us today, and keep questioning the technology that powers your world.